Okay. Thank you very much, Cecilia. I feel like a flight pilot, so this feels really cool. Either that or a DJ operator, so excuse me if I'm getting used to my new role. Anyway, first of all, I'm delighted to be here back in Brazil, in this beautiful place. Thank you very much to the organizers for making it happen. I'm also really impressed with this building and the light and the airflow and all of that, so everything's wonderful. Thank you very much. All right, what is the interplay of quantum criticality with first-order phase transitions? This is a question that my friends Piers and Musio, who are here, and Gil, who's here in spirit from Cambridge, who's our experimental colleague, who's well connected with nature, have been asking. And I'd like to tell you about our project and our ideas about what we like to call quantum annealed criticality. Experimentally, there are a number of systems, compressible systems, that show lines of first-order phase transitions, okay? And yet still indicate quantum criticality. Naively, we might think that if you have a classical first-order transition, you might have quantum first-order transition. But what seems to happen in these systems is that classically we have discontinuous transitions, and yet we have evidence for quantum criticality. And so our project was to try and develop a theoretical underpinning for this phenomenon. It's well known that strain energy density coupling leads to first-order transition classically. And what we decided to do was to generalize this so-called Larkin-Pitkin criteria to see what happened quantum mechanically. In a nutshell, we found the following phase diagram. If we look at temperature, and then if G is a quantum tuning parameter, for example, pressure, and then if we have a field that's conjugate to the order parameter, in the case that we'll be discussing, the order parameter's polarization, so electric field, what we find is we have a line of first-order transitions that can be classically, we can get a classical critical points if we apply fields parallel and anti-parallel to the order parameter. And then we have a quantum critical point. Oops. So what we have is we have a line of first-order, a sheet of first-order phase transitions bounded by these second-order lines. So that's what I'd like to tell you about today. Now, just to put this in context, what's been known about this question before, the interplay of quantum criticality with first-order phase transitions? Well, there's some beautiful work that involved our collaborator Gil Lonzerich, which actually had the opposite situation, where at t equals 0, one had first-order transitions in magnetic metals, first-order transitions. Then one had thermal fluctuations created a tri-critical point, and it went continuous. And we had then a sheet of first-order transitions where if one was interested in actually accessing a quantum critical point, one had to apply a field. So in this system, one has temperature versus tuning parameter, which can be pressure or field. We have a first-order transition coming up to a classical tri-critical point, and then a second-order transition. So what we're interested in is, in some sense, the inversion of this. Okay? All right. So let's just remember, particularly for those of us who are students in the audience, let's just remember about classical and quantum phase transitions. Classical transitions, of course, the dominant energy scale is temperature. And in a classical phase transition, temperature is then the tuning parameter. And at a classical second-order transition, we have a correlation length that diverges. Now, at a quantum phase transition, temperature is not the dominant energy scale. We have a frequency. Here, of course, being the theorist, I'm assuming all fundamental constants to be 1. Okay, so we have a frequency that's a dominant scale. The frequency is larger than the temperature, And therefore, of course, dynamics will be important. So in this case, temperature is not the tuning parameter, it's something else. In this case of lithium holmium fluoride, that was studied a lot by Tom Rosenbaum, Gabe Epley, and their collaborators, there is a transverse magnetic field. It can be pressure, it can be lots of other things, but it can't be temperature. So here we tune, in this case, with transverse field. We have a correlation length that again diverges, but now because dynamics are important, the effective dimension is d, the spatial dimension, plus z, the dynamical exponent associated with the dispersion. That is, omega goes like q to the z. Okay? So that's what a quantum phase transition is. All right, onward. So let's go back to the previous scenario. In the previous scenario, how did it work? At t equals 0, we have a first order phase transition. Now, how do we get a first order phase transition? If we look at the lower energy effective action, what it means is that the quartic term coupling the critical fluctuations has to be negative. So the quartic term is negative. In this case, it's due to magnetic excitations coupled to particle hole excitations. All right, so it's originally negative, but then as you increase the temperature, thermally induced order fluctuations drive it positive. You have a tricritical point where it's 0, and then you have a U effective that's positive. And this was originally discussed in this paper by Gergara et al. In the context of strontium ruthenate. Turns out there are many systems that have this, and there was a beautiful review article by Brando et al. In 2016. This is just one example, temperature versus pressure in this case. This is second order, then it goes first order coming down to here, and you see these nice signatory wings where we have a tricritical point, then we have quantum critical endpoints. So if we're interested in quantum criticality in these systems, we have to apply a magnetic field in addition to the pressure. So that was the setup as it was. Now, let's talk about our experimental motivation. Our experimental motivation comes from a completely different area, the area of ferroelectrics. Okay. Now, ferroelectrics are systems with spontaneous polarization. The poster child is barium titanate, shown here, where the polarization is due to the displacement of the titanium. Okay. Turns out in these systems, there's very strong electromechanical coupling. They're first order. Here we see polarization as a function of temperature, very sharply first order. And yet, if a field is applied, we can drive the first order transition to a classical critical point. And so we have two classical critical points, depending on whether you apply the field parallel or anti-parallel polarization. So this is classically first order. Now, close cousin of barium titanate is strontium titanate. Strontium titanate is not quite ferroelectric. Okay? The dielectric susceptibility goes up, 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 but it never actually becomes ferroelectric. Okay, however, it can be nudged, tweaked into being ferroelectric, for example, with a little bit of pressure, or even substituting oxygen 18 for oxygen 16. So in fact, oops, if you substitute oxygen 18 for oxygen 16, it becomes fully ferroelectric. But what you can do is you can also actually just add a small amount, and you can drive it to a quantum critical point. And this quantum critical point is seen by a diverging dielectric susceptibility, but more to the point, if one looks at the Grunheisen ratio, which is the ratio of the thermal expansion to the specific heat, which is a signature of quantum criticality, one finds that it actually goes as 1 over t squared, which is what's predicted in this system. So the question is, here we have strontium titanate that is classically first order, and yet it's showing quantum criticality. And indeed, it turns out that there are a number of systems like this. Here we have our our standard favorite ferroelectric, barium titanate, which it turns out, under pressure, seems to indicate some quantum criticality. It's only recently been studied. I remind you that most of these ferroelectrics are studied for room temperature applications. Most experimentalists who study ferroelectrics don't actually have a fridge. So one of the things that Gil has been trying to do, and many others more recently, including Karsten, who's here, who's been doing some nice pressure work on these systems, is actually, what if we take these materials that are used for room temperature applications and what if we go to low temperatures? What can be learned about quantum criticality? And one of the points that Gil, as our experimental colleague, always emphasizes is notice, for example, in barium titanate, we have a range of about 400 degrees. So here we have a range of 250 degrees. And because these systems are tremendously lattice sensitive, he tells me that in fact you get the range of temperature for an order of magnitude less pressure than in magnetic systems. So the question that he's been pushing us on is, do we have a theoretical understanding for a compressible system that shows first order classical behavior but seems to indicate quantum criticality? All right. So what we decided to do was, we knew about the Larkin-Pitkin phenomena. This was actually developed for magnetism, but we decided that we would look at it both for magnetism, for compressible systems, both magnetic and ferroelectric. What happens in the Larkin-Pitkin phenomena is we have an interaction with a strain with a fluctuating order parameter. Okay, so let's just review how this works. Let's first go through it conceptually. We have a system that has a diverging specific heat in a clamped system. Clamped system means I have fixed dimensionality. Then I unclamp it. It has a first order transition. This is due to a strain energy coupling that we'll talk about in a minute. And what's the Larkin-Pitkin criteria for first order transition? The Larkin-Pitkin criteria is that the effective modulus, which is a combination of the bulk modulus and the strain modulus, has to be less than the specific heat in the clamp system over the transition temperature over the strain derivative. This is dTc d log v, and the shear strain is crucial. So it's always first order classically. In other words, we have coupling of the uniform strain to the energy density. Oops, I don't know what happened. Sorry about that. I'm a theorist, as you see. Anyway, a coupling of the strain energy density, and we have a macroscopic instability of the critical point, and then we get a discontinuous phase transition. So what we set out to do is to ask, can we generalize this to the quantum case? So in order to do that, we need to rewrite the Larkin-Pitkin criteria in terms of correlation function and response functions. So let's take the simplest case, isotropic elasticity in a scalar order parameter. Now our interaction will be coupling of the order parameter, which is phi squared, coupled to the volumetric strain. Now this is the reason we choose coupling, is because our order parameter, whether magnetization or polarization, breaks the symmetry, so this will be the leading term. Later this week, we'll hear about a different kind of strain coupling from Indranil Paul, who will tell us about pneumaticity and strain coupling there. Okay? And that produces very rich results. But this is the coupling that we're going to consider. Okay. The elastic degrees of freedom are Gaussian. Okay? So we want to integrate those out, but it has to be done very carefully. Why does it have to be done very carefully? Because it has to be divided into two terms. And this is following very closely the Larkin-Pitkin paper. There's one term due to the fluctuating atomic displacements, and the other term due to the boundary conditions. A Q equals 0 term and a finite Q term. So what happens? When we look at this term would be 0, would not be there in the clamp system. So basically what happens after a fair amount of calculation is that we integrate out finite Q version, we get short-range interactions between the critical modes. However, integrating out the Q equals 0 part induces an infinite range attraction between the critical modes. And that is what was responsible for driving the first order transition. Okay. So again, the way we're proceeding is we're taking a clamped system that has critical fluctuations, we're unclamping it, and we're asking whether that critical point is stable. Okay. So what happens when we want to generalize this to the quantum case? Well, now we have to sum over all possible space-time configurations. We write down the strain as a static, uniform Q equals 0 part, but now we have finite Q, finite frequency part to the strain. We have to do our Gaussian integral, again, very carefully, but what we do find is that actually we induce an infinite range interaction between the quantum critical modes due to a classical uniform strain field with the same renormalized modulus that we got classically. So in a nutshell, we get an effective action. It looks like this, where here we have the effective modulus, and our Lagrangian, for simplicity, is just a phi-4 theory. Okay, and then we look at the partition function of the unclamped system. The renormalized modulus will then be of this form, where kappa tilde is kappa minus this correction term, and that's going to be of great importance to us. In the classical limit, of course, we have no time dependence, so we can write it in this way. And now we're very interested in what this correction is. And in fact, these are just energy fluctuations, so we see that we get a recovery of our criteria. And indeed, what we find is that kappa tilde is less than 0. If the effective bulk modulus is less than 0, that means we have a macroscopic instability. Okay? And so we have a first order transition. And so this is just another way of thinking about the Larkin-Pitkin criteria. All we've done so far is rederive the Larkin-Pitkin criteria. Again, when the specific heat diverges, then if we find that that we'll have a first order transition. And this work was first done in 1969 by Larkin and Pitkin. Then a beautiful renormalization group discussion was followed by our colleague Joe Sachs at Rutgers. But the approach that we're taking now is very much following Bergman and Halperin. Assuming a classical critical point in a clamped system, then unclamping it and asking, does that critical point survive? And the signature for seeing whether it survives is to see whether the effective bulk modulus stays positive or goes negative. Okay. All right. Now, we can actually also derive this using a diagrammatic approach. Okay, so what we're interested in is looking at the quartic term in the low energy effective action. And the quartic term will have the bare term plus the term due to this classical strain interaction, infinite range. And we can write down a Dyson equation for the strain propagator that looks like this. And what we find then is that the renormalized effective modulus, the renormalized bulk modulus, is kappa minus tilde kappa, and this delta kappa is lambda squared. That's the temperature derivative, the strain derivative of the transition temperature, times a susceptibility, which is the Fourier transform of the order parameter fluctuations. Now, the key point I want to make here is that the key thing that determines whether or not we have a first order transition is whether or not this correction diverges. It's somewhat counterintuitive because normally you think of a divergence associated with a second order transition, but here the key point is that if delta kappa diverges, then that means that kappa tilde goes negative. Okay? And so it's the infrared properties of this correction that are very important in determining whether or not we have a first or second order correction. Thank you. So, classically, for this very simple case of a scalar order parameter and isotropic elasticity, we always have a first order transition. What happens quantum mechanically? Well, the best way to see what happens quantum mechanically is to look at the long wavelength behavior of this correction. Exactly what we do. We can look at it in the Gaussian approximation to tell us what's going on at long wavelengths. When we look at it in the Gaussian approximation, we can do basically power counting. Chi goes as 1 over q squared. The frequency goes as q to the z. So then the limit as t goes to 0 goes as q to the z plus z over q to the 4. So in other words, it's non-singular for d plus z is greater than 4. Okay. So what we're finding is that the correction to the renormalized bulk modulus is not universal for d plus z greater than 4. So, in other words, 0-point fluctuations toughened the system against a macroscopic instability present classically. Okay? In other words, if you want to be dramatic, you can say that quantum fluctuations lift the system from the infrared slavery that's in the classical regime. Okay, so that's why we call it quantum annealed criticality, because of this toughening. So, for t, what have we found? For t greater than 0, we have classical first order transition. For t going to 0, we're saying that we have non-universal for d plus z. Going to 4, we have a phase diagram that's in some sense the inversion of the other scenario. We have 2 classical critical points. We have a quantum critical point. We have a sheet of first order transitions. For those of us of a certain age, looks a lot like a Rolling Stones cover, but in any case, and that's where we are. Now, what's the experimental setting for this? Well, because we have non-universal corrections, we have to consider case by case. But one possibility which motivated this in the first place are quantum ferroelectrics. Ferroelectrics have z equals 1. That means that omega goes like q. Okay? And so they're in the marginal dimension, because that means d plus z, since they're 3-dimensional, equals 4. Okay? However, I should say that the logarithmic corrections we don't expect to be singular, and they have not been observed experimentally to date. Okay, so what are experimental probes? Grunheisen ratio, I already mentioned that with strontium titanate. Hysteresis. Future work. Multi-component order parameters. Okay, that's a little bit trickier because the specific heat exponent is crucial for a scalar order parameter. It's positive, but it'll be negative for multi-component order parameters, and so that probably means that we expect classically a tricritical point. Elastic anisotropy, that's very important in these systems. Domain dynamics, disorder, specific physical settings, order transitions, and of course metallic systems. So, just to conclude, sorry about the technical hitches, just to conclude, so we have time for questions. We've generalized the Larkin-Pitkin criteria to the quantum case in the simplest circumstances of a scalar order parameter with isotropic elasticity. We find a phase diagram where we have a temperature tuning parameter field, here electric field, where we have a sheet of first order transitions that looks like this. And for us, the most exciting thing about this is that it's theoretical framework which tells us that just because we have a certain order transition classically doesn't mean we have the same thing quantum mechanically. And in particular, one of the reasons that we're very excited about these possibilities in these compressible materials is they provide new lattice-sensitive settings for the exploration of exotic quantum phases in both magnetic and in ferroelectric systems, where temperature ranges, broad temperature ranges, can be accessed with reasonable pressures. So, on that note, I thank you very much. I should say that that I'm looking forward to a week of stimulating talks. This project, I should say, came from my last visit to Brazil, and I'm looking forward to the projects that come out of this one. Thank you very much.